Hello everyone, I am Zheyuan Zhang, and I come from Northwestern University. Today I would like to introduce our recent work, Domain Generalization with Correlated Style Uncertainty. As we all know, in practice, a distribution shift between training and testing always exists, which raises a very challenging problem for real-world deep learning applications. Many domain generalization algorithms have been proposed to address this challenge in recent years. Particularly, style augmentation, which takes advantage of instance-specific feature statistics, can be used to generate novel domains while preserving the structure information. This method has been widely used for domain generalization. However, all previous works, like mixed style or DSU, ignored the correlation between different feature channels or only limited the style augmentation through linear interpolation. Here, we calculate the correlation matrix between two style statistics from PACS datasets, and we observe that the correlation matrix of style statistics, regardless of the mean or the standard deviation values, is not diagonal. Indeed, a strong correlation exists among the channels. We applied eigenvalue decomposition over the calculated correlation matrix and found that very few eigenvectors dominate most variants, as shown in the bottom row of the figure. The correlation matrix indicates that the combinations of feature statistics are not arbitrary but limited by task objectives and training procedures. Most variances happen within the specific principal directions. Arbitrary augmentation over the style statistics might damage the training itself. Based on this motivation, here we propose CSU, which is a well-calibrated framework that goes beyond the interpolation strategies by preserving correlation between different feature spaces. Our proposed CSU contains two parts: decompose the feature covariance matrix and synthesize correlated Gaussian noise from the standard Gaussian distribution. Specifically, given the intermediate features extracted from the network, we first estimate the covariance matrix of feature statistics and decompose the covariance matrix using eigendecomposition. Based on this decomposition, we could generate correlated augmentation from the standard Gaussian distribution that shares an identical distribution as the original domain. Then, we update raw data feature statistics by adding this correlated augmentation. Finally, we restore the feature statistics back to the normalized features and achieve the augmented features. We validate our model's performance on various multi-domain classification tasks, including PACS, Offic-Ahome, Came-Leon 17 and the Duke Market 1501 instance retrieval task. Experiments on these datasets obtained significant margin improvements over the SOTA methods. Experimental results on the PACS multi-domain classification task achieve highly significant improvements over the baseline in the art, cartoon, and sketch domains, as 14.3%, 5.6%, and 12.2%, respectively. Similar performance gain is also achieved in the office home classification task. CSU also achieves around 26.9% and 19.6% advancement over the baseline in map value using the ResNet 50 model in the Market 1501 to Duke and the Duke to Market 1501 experiment, correspondingly. Likewise, CSU achieves around 20.1% and 24.2% improvement for the OSNet model experiment. We could also observe similar advancements in ranking accuracy, and CSU achieves impressive improvement over other methods. To answer the question of where we should insert the CSU, we conduct comprehensive experiments on the PACS and Office Home datasets using the ResNet 18 structure. Inserting 6 blocks of CSU in all potential positions achieve the best results for the PACS dataset, while inserting 4 blocks of CSU in the last 4 positions achieves the best results for the Offic-Ahome dataset. As described in the previous section, the hyperparameter alpha determines the intensity of augmentation during training by manipulating the shape of the beta distribution. Here, we show the influence of alpha on the PACS, Office Home using the ResNet 18 structure. Similarly, to avoid the influence of different inserting positions, we insert CSU block in all positions for every experiment. We select alpha from 0.1, 0.2, 0.3, 0.4, 0.5, 0.7, and 0.9 for one comprehensive experiment. We can find that a smaller number of alpha 0.5 always performs better than the relatively larger number. Based on these experiment results, we recommend selecting the alpha from 0.1, 0.2, 0.3, and 0.4, and the best configuration may vary according to the tasks. We also provide 2D visualization of flattened feature maps. We can clearly observe that the trained model can effectively obtain more domain invariant feature representations. Thank you for your listening.